right, guys, so we are ready to start. Last week, we did the bottleneck methods. When we talked about creating a neural network in which the input layer and the output layers are wider than the intermediate layers. In particular, if you have a latent representation layer of a much lower dimensionality, then the neural network is forced to learn a representation that is a summarized representation of the data. A more technical way we say it is that when you create a bottleneck, you force an efficient representation to be learned. Now, the uses of this are broader than just what we are going to talk about today, or the lab of today, word embeddings. Those are called autoencoders. Autoencoders essentially, for example, in the simplest form, you take an input and you try to reconstruct the input, except that the data passes through this bottleneck, this layer, which is of much lower dimensionality. When you do that, you end up learning a representation. When that representation is stable and robust, it leads to a lot of benefits. For example, it is data compression in its simplest form, very efficient data compression. It can be also used to, for example, denoise data. You take data, you add deliberate noise to it. Then you feed it in, but at the other end, you compare the output with not the noisy version of the data, not the noisy version of the image, for example, but with the clean initial original image. And you create a loss function based on the gap between x and x prime. So suppose you say x is the input, and let us say you add some form of noise, and then it becomes x tilde. X tilde goes into the autoencoder, and what comes out is y. So you don't look for the gap between x tilde and y. You look for the gap between x and y, the original x and y. And you try to do a gradient descent and backpropagation to minimize a loss function that is the mean squared error between x and y. When you do that, you end up learning a very efficient representation that is stable. You come up with something that sort of learns to remove the noise from the data. That is a denoising autoencoder. Another example that we took is you can do a patching. You deliberately hide a piece of the image. You take an image and some little patch of the data, the image data, you sort of mask it and you feed it in. But then you again do a loss function with the original image, output in the original image, and you basically force the autoencoder to reconstruct or fill in the blanks in the image. And that leads to also a very good reconstruction effort. Now, this ability to not only reconstruct the original, but also to fill in the gaps, right? To interpolate the gaps is very powerful. Somewhat along the idea is one more thing which I didn't allude to last time, is that you can amplify the resolution of an image by using a technique called super resolution. You take an image which is maybe coming from a smartphone of lower pixels, and then you try to you create a super resolution version of it. Let's say that it is a 5 megapixel. You're trying to create let's say a 20 megapixel picture of it. As you know, given pixels, it's very hard to create a super resolution version because that ends up introducing a lot of noise. And people have tried to interpolate various techniques to interpolate in between, and that leads to sort of a smoothing effect. One of the things autoencoders are very good at, as we are finding very recently, is that they can help you create super resolutions, versions of images in a very plausible way. So that is another thing you do. Then the next thing is you can do sparse representations. So given a data, if you build a neural net that has more, whose autoencoder in which the bottleneck layer encodes actually has more nodes than counterintuitively than the input and the output, but you force most of the nodes to be silent, on only some nodes to be fired, that's your sparse autoencoder. Again, it leads to sparse representations of the data. So these are all ways of deriving efficient representations of the data. Now, continuing the same idea, but taking a slightly different approach to the loss function. When you bring it to NLP, you ask this question. Suppose I give the context of a word. Let us say the cow jumped over the moon, right? So jumped is the word, the cow over the, right, is the context, the two words before and after, let's say, or three words before and after. Whatever you choose, you take the surrounding words and you say, this is the context, and I want the system to predict the basic, something like an autoencoder, but I want it to predict the word jumped, right? When you do that, this is the continuous bag of words approach. You feed in the context and you expect the word to be the one that whose probability is the highest. To do so, or when you do so, you are creating a word embedding because the latent representation will be of a much lower dimension. For example, a typical vocabulary can be 100,000 word vocabulary in a corpus. Let's say the English language, if you take a sufficiently rich corpus, let's say the Wikipedia or something like that, or the Google News, you will end up with millions of words and or hundreds of thousands of words. And that is exactly the lab we are going to do today. Then when you create a representation that is only in terms of 25, 50, 100, 300 dimensions, that's a very, very efficient representation of the words. Remember, as I mentioned, in the original space, the words are all orthogonal. One hot encoding means every two words are orthogonal to each other. The dot product between them is zero. The point of learning these representations is they capture somehow the semantics of the language. So we talked about the example, like for example, a banana and an orange should be near each other, but a banana and a tractor should be pretty far off. And that sort of a vector distance or distances in the vector space, latent word embedding space, should convey semantic distances. So the thing that got people very interested around 2014 and so was that when you use this kind of bottleneck architecture and you create a loss function in the way we discussed last time, you learn these so-called word embeddings, lower dimensional representation of words, which are semantically rich. You can do things like a king minus man plus woman is equal to approximately queen. And we'll see that today in the lab. Or you can say Italy minus Rome is approximately the same as France minus Paris. Right? So you can see the relationship between country and capital. Also, you can do analogies, the sort of analogies that I suppose show up in standardized tests quite often, that Italy is to Rome, then what is to Paris? And then the answer should be France, and so forth. And we can see whether these analogies work or not. And also, if you encounter a word whose meaning you don't know, you can ask for the nearest match, and therefore you can infer the meaning of the word by looking at the nearest match. Now, all of this is impressive. It sort of works. I wouldn't say that it perfectly works. Um, it has a few problems, and today I'll mention those problems before I continue. One is the so-called alignment problem. There is a book that has recently come out. It is literally called the alignment problem. What happens with this sort of embeddings is you derive it out of corpus of text. A sufficiently large corpus of text is likely to have social prejudices, social biases, archaic beliefs, and things like that. And in many ways, when you take a corpus like that, like let's say sufficiently large collection of web articles, or websites, web pages, and then you build a word embedding, you train a neural network to learn a word embedding, you sort of perpetuate and immortalize such biases, such archaic beliefs and stereotypes. So that is the alignment problem, and it's a pretty persistent problem, and we should watch out for. We cannot get too excited about word embeddings. Um, at best, it's an imperfect tool. At worst, actually, it can be pretty misguiding in its solutions. So with that being there are many techniques for doing word embeddings. We did the first one that I explained was the continuous bag of words. You feed in the context and you expect the word to come out. The second technique we learned is the opposite of that. You take this technique, turn it upside down. This time around, you pass in the word and you expect the architecture, this encoder decoder architecture, to essentially predict all the context words. So this is your skip gram model. We built it by taking actual examples, positive examples of neighboring words for a given word, the context words, and negative examples by just randomly picking words that quite likely are not going to exist next to this word. And those become your negative samples. Therefore, then train it using your standard cross entropy laws for a classifier. When we do so, you have the skip gram with negative sampling method of generating word embeddings. People usually just call it the skip gram model. A third way we learned, which was using the co-occurrence matrix directly, and that was the glove embedding. Now, all of these are directly or indirectly related to the co-occurrence of words together, or the co-occurrence matrix, but this glove embedding tends to use it in a more direct way that we talked about last time. So I wouldn't go into glove. Glove has a more global representation of a word. In general, skipgram outperforms in most situations word to vec. Word to vec is the least performing in many ways. Glove does, and skipgram does, sorry, continuous bag of word is the worst performing generally. The skipgram does better than continuous bag of words, and glove does in general much better than both of them. However, it's not always true, and so you should try it out, play with it, and see what works for you in your given situation. Now we'll come to the lab or the practical uses of it. See, when you have word embeddings, you can either import a word embedding that has already been trained. So Google and so many, Facebook, etc., they have released fairly well-trained word embeddings that has been trained on massive corpus of data, different corpora of text. And these are general purpose corpora. They're not specific to a domain. Like, for example, they're not specific to law and lawyering or medical and so forth. They're general purpose. So, and they capture the human language, the common human language very well. People have created these embeddings now in many, many languages, and the number of languages in which these embeddings are available, pre-trained, is growing. So given the fact that you have these word embeddings, you could just adopt it as is, and then you can do your work. Like, you have a vector space representation of a word. Now that you have a vector space representation of a word, you can do just about everything you do in standard machine learning. Remember, machine learning or AI is essentially a box into which you feed in vectors belonging to some Euclidean space, right? Some are to the p-dimensional um, vector, right? You feed into that a whole bunch of them, and so you feed in data. And you can either do pattern recognition, for example, you can do clustering, dimensionality reduction, and so forth, topic modeling, and so on and so forth, we saw for text. Or you could be doing supervised learning, in which case you're doing classifiers and regressors and so forth. Right? But the one basic requirement is everything finally must look, when it goes into our machine learning models, it must look like a vector. Right? Every input must look like a vector belonging to a p-dimensional vector space, where p is the number of features that you have. Or if you do one-hot encoding because they're given a feature is categorical, then it will be more than p, but you essentially feed in vectors. So having word vectors, especially of low dimensional representation and semantically rich, opens the door to a lot of machine learning, to classification, to this, to that, and many things. So today we're going to take some very simple examples. This is likely to be the easiest lab that you folks have done. I expect that we'll finish the class relatively soon, which should be a change because the last few weeks we have had classes that have gone on till 10:30 or 11 sometimes. So today, for a pleasant change, we'll have a rather short lab. Are you guys looking at my screen?
Yes, sir.
Guys looking at my screen? Okay, thank you. So as you look at this screen, you see that this is one file. I put it there on your course web page. The course web page, it says, where is it? Hang on, the course web page says, let me go here, labs and, where we go? Yes, do you see word embeddings, the last item? It is this time I've just given one file because it's a simple lab. I didn't see the need to upload the entire project. And it also shows that word embeddings are very easy to use. So let's come back and could you guys tell me if, sorry, the text is clearly visible? Is it legible on your screens?
Yes.
Yes, sir.
Very
Yeah.
nice.
Right, all right. So we are importing, this is a very basic import. I don't want the notebook to get cluttered with all sorts of deprecation warnings and so on and so forth. So I removed that. Now, one thing I had to do to run this, which was unexpected, is I had to install a library called PyEMD. Your mileage may vary. If you don't have to install, all the better. If you have to, then just go ahead and install this pip install PyEMD. Right. Now we go and import Spacey. Just to recap, Spacey is our industrial strength, high performance natural language processing library that we have standardized on. So let us review what we did. The line number 4, it says Spacey load a model. If you notice, this model is an English core of the large kind. It's a large model, LG, right? So that means it comes with word embeddings and so on and so forth. And just to whet your recollection, if you do the small model, which is quicker to download, that won't contain the word embeddings. Are we together, guys? Right. So that is that. And then the next line, so what happens is when you load it, what do you get? NLP is what? NLP is a model, right? It is, think of it as a NLP, natural language processing model, species model. Now to this model, if you feed in a text, I put a text here, the cow jumped over the moon, the little dog laughed to see such fun, and the dish ran away with the spoon. You take a sentence like that and you feed it to the NLP model. What will it do? You get back a document. What is that document made up of? Document is a stream, is a sequence of tokens, isn't it? It parses that, NLP, Spacey will parse that, and it will understand, it will go through the pipeline. Actually, a better way to think of NLP is not a model, it is the pipeline of things that you can do, or the NLP operations that you can do. That includes, cleaning up, checking whether it's a stop word, then lemmatization, right? You remember, lemmatization is taking every word and converting it to its standard form, right? And thus we do that. Just to, do we guys remember what lemmatization was? Maybe I'll just add lemmatization here, token. Somebody please say that again.
It gives the root words.
Is the root word. So let's see, just to whet our recollection, let us see what it means here. And yes, See, you notice that they have all become small letters, and jumped has become jump, right? Most of the words remain the same. Little dog. Laughed has become laugh. Ran has become run. So all the words are um, reduced to their root word, right? So they're standardized. That's the process of lemmatization. Then the other thing is we check whether the token has a word vector in this model or not. It does have, right? And what is the size of this? What is the norm, the vector norm, the size of it? They're all pretty much the same, but there it is. And sometimes a word can be out of vocabulary. For example, let's try the same word, and I will now introduce a word, a common large word that we tend to use, heteroscedasticity. Right? Suppose I add this word. Now, what do we expect when we try to do this? Can you guess, guys, what will happen? Yeah, if you observe very carefully, the heteroscedasticity, is it a out of vocabulary word, or OV, the last token is out of vocabulary. So it is saying that this language model has never encountered the word heteroscedasticity. Are we together? And why is that? Certainly, heteroscedasticity is a valid English word. It's a technical term. The point is, every vocabulary, if you remember, we're limited to more frequent words. If a word occurs only once or twice, we tend not to include, or infrequently, tend not to include it in our vocabulary just to keep our TF idea vector of a reasonable size before we go into word embeddings. Right? So I hope that just is a good refresher of what we did before. Now, if you want to know what is the dimensionality of these words, I just take, there's a little bit of a thing. By default, spaCy will create a very large word vector of 300 dimensions. 300 dimensions has sort of become the standard ever since Google first released the word embeddings of 300 dimensions. But we're going to play around and see what other dimensionalities we can use. So while it is good to be able to do that with spaCy, in my experience, GenSim is actually a little bit richer as a library when it comes to word embeddings. It is good for both word embeddings and for topic modelings. If you remember, last time we used GenSim.
As if spaCy does word to vec, or what does it do?
Yeah, spaCy does word to vec and glove, both.
But you didn't mention whether it was word to vec or glove in that previous.
Yes, that
by
is.
default it is word to vec.
In this particular case, actually, you can assume that by default, spaCy, if I'm right, is glove.
Okay.
Right? Is glove, if I remember right. And you can check, actually, it tells you some metadata information. So next we go to GenSim. GenSim, and now we'll see in GenSim how you can play with different word embeddings. You can, for example, and in fact, this is your lab assignment. I'm giving the example with word to vec. What happens if you change it to fast text, or what happens if you change it to glove? Right. Those are the things we'll try in this. So with GenSim, the first thing we'll do is just to give you a taste of how we do things. I'll take a very small list of sentences. The sentences are broken up into words. Each line is sort of a sentence of sort. So you look at this so-called sentences in which all the stop words have been removed. This is the toy data set. Common text is a toy data set that is there. And it is deliberately handcrafted by somebody with so many words. So how do you create a word embedding out of this? What you can do is you can take this vocabulary, or sort of this corpus of sentences, and you can feed it into the word to vec constructor. The word to vec comes in GenSim. Do you see gensim.model? And by the way, import, instead of word to vec, you can do glove, you can do fast text, and so forth. So should you do all of that, then you can start training it. The interesting thing with the constructor here is this is a one shot, like it does everything. It builds the vocabulary, So let's parse it. Sentences is equal to common text. So what it means is this is the array of sentences. Size is equal to 100. The size tells the dimensionality of the embedding space that you want, 100 dimension, which in this case is an overkill because we don't even have 100 words. But this is a toy example. A window is 5. Could somebody remind me what is window from last week's discussion?
That sliding window around the
Yeah,
word.
exactly. And why do we keep it as odd number?
So it's in the middle.
Entry
That's
word
right.
Middle element.
Yeah. So you have symmetric, there's so many elements to the right and the same number of elements to the left. Right? So if you have jumped and window size is 5, then the cow is on the left, over the is on the right. So you can pick up those symmetric amounts. Now, minimum count is a count like what is the minimum number of times a word has to occur in the vocabulary to be, has to occur in those sentences before you take it into the vocabulary. 1 means you always take it in, right? Workers is equal to 4. That's just a way of how much you want to parallelize and so on and so forth. We'll ignore that. And the thing is, once you build a model, now here obviously it's a very trivial uh, corpus. So it takes 17 milliseconds to build the vocabulary, build the model, word-to-vec model. But in reality, when you run on a massive corpus, it takes a very, very long time. And when it takes such a long time, you want to save it and you want to share it with your friends. So let's just say that you are creating a special word embedding for some domain. Let's just say you're creating a word embedding for legal, for lawyers, or you're creating it for doctors, or you're creating it for the domain of human resources and learning and so forth. What you want to do is you want to create a custom corpus which contains all the sentences that you do find in your domain, and then train a custom word embedding. Now, what are the advantages and disadvantages of training a custom word embedding? The advantage is it may outperform a general purpose word embedding. The disadvantage is, as I said, it may. Quite often it doesn't, because to train a word embedding takes actually a lot of data. And if you don't feed it a lot of data, it doesn't learn very well. And that is something I'm going to show you in a little bit in this lab. So be careful when it comes to this classical methods. Be careful and don't be sure that just because you have your own specific domain, you can create a better word embedding than one of these pre-trained word embeddings. And the reason is the pre-trained word embeddings has been trained on a truly gigantic amount of text, whereas if you can't marshal that amount of text from your sources, you might not be able to get as good a word embedding. Now, there's something else that you can do that sometimes people do, and that is you can take a word embedding, a general purpose word embedding, and then on top of that, you can augment the training with your custom domain, and that is effective. Right? So what you're doing is you're doing what I would call sort of a transfer learning kind of a situation. You're taking a word embedding, adding more text to it that's specific to your domain, and so you amplify the relationships and customize it to your things. It's a last mile of fine tuning it. That is a good idea. Right? So you can play with that, and we will do that. So here, this is a simple, I wanted to show you how rich these libraries are. Just the constructor takes care of building the word embeddings. Right? After that, you can save it, and then you can load it and play around with it. Now, there is one thing, this word embedding model, it is a word embedding. I called it model, I could have just said word vectors. It contains in it a member variable called WV. These are the keyed embeddings, keyed words, keyed vectors. So there is a subtlety here. This is specific to GenSim. if you look into model.wv, that is a much more sparse representation. It just contains the word and their vectors. It doesn't contain a lot of other things. So if you want to work with speed, it is a better idea to use the model.wv rather than model itself. You would get exactly the same semantics or the same results, but model.wv is a little bit faster, much faster actually, because you're working with things that load into memory much faster and more efficient when you're doing a lot of comparisons. Now comes an interesting thought.
Asif, one
Yeah.
quick question before we build further. Common texts, what did it contain? What was the corpus in common text?
Literally what is staring you in the face here.
Just that.
Just that. It's a toy data set. Remember, it's a toy corpus. Right? It is just to illustrate that you can do word embedding on just a few sentences if you so choose.
Okay, thank you.
And also for it to run on those people's machines who are working with dinosaurs, like if you have, I don't know, a laptop that is 5 years, 6 years old, it will still work on that without GPU support and so forth. So if any one of you have a laptop which has just something like 8 gigs of RAM and a magnetic hard disk and a Core i3 and so forth. So, you know, you always want to have some code that will work anyway. So this is that code. So now model.wv is a more sparse, is a more efficient sort of a high performance version embedded inside the model. If you work with that, that's the advantage. It works faster. There is, however, a downside to this. The downside is while the model can be augmented, remember I said that you can take a model and you can train it, you can extend the learning with more sentences, right? You cannot do that with model.wv. That is an immutable object. The moment you call model.wv, what you get is an immutable representation which cannot be further trained. Are we together, guys? That's the difference between model, the big object model, and this very compact and more memory efficient representation, which is model.wv. WV stands, of course, for word vectors. Are we getting this subtle point? It is just a speciality of GenSim. There's nothing theoretical or deep about it. It's just a way to get your work done faster. But the subtlety is one is immutable while the other can be further trained with new sentences. Right? So in this very simple word, if you notice the word computer appears here, it's next to human interface, computer is next to user and system and so forth. So if you go into this and you say, okay, give me the word computer, what does it look like? It turns out you ask for a 100-dimensional representation. So, well, you get 25 rows. This is 100 elements, a pretty big array of numbers. The only reason I'm showing you this is to show you that whether these numbers may or may not mean much to you, just eyeballing it, it suffices to say that it does look like a single vector, isn't it? It looks like a vector in a 100-dimensional space. All of these elements are floating points, real numbers. Right? So it is real to the 100-dimensional real space.
See,
So
one quick observation here is if you look at the corpus, the common texts, that didn't even have 100 words. So you literally actually
yes.
expanded it.
Yes, you have expanded it, which is why, I mean, in reality, you would never do it. It is just illustrative, right? And obviously the learning here is not very efficient at all in any way. Also, you can't really learn from such a small corpus. It's a toy exercise, just as a warm-up. So now let's go to something a bit more realistic and practical in life. So as I said, it is for your purposes in NLP and machine learning with text, it is usually wiser in the beginning to start with a pre-trained model. This again goes to the point of transfer learning that I keep talking about. So go with a pre-trained model, and all of these libraries come with pre-trained model. I think if there's one thing we have learned, it is that most industrial strength libraries now give you lot of pre-trained models that you can use in every domain, whether it is image processing, and we are talking about VGG and AlexNet and Inception and so forth, or we are talking about transformers. We saw a lot of pre-trained transformers, very hard to train, but trained transformers, birds and all that. And here in the space of word embeddings, you have a lot of word embeddings that people have created. Now, a small list that GenSim comes with is this. You can go to GenSim and you can say, give me a list. So GenSim downloader, what it does is that it downloads from the internet, from standard locations, some pre-trained word embeddings, right? So it's actually a short list of what comes built in with it, but it doesn't prevent you from going and getting more word embeddings. And by the way, people keep coming up with new and new ways of doing word embeddings. In the class course portal, I've given entire sections on word embeddings, and people have awesome word embedding papers and so on and so forth. Very active area of research. So anyway, so here it is. Given the models, you can get all the list of the models. So what I'm doing is I'm getting the list of the models and printing it. This code is nothing fancy. It just prints this table, right? In other words, this models object that is there, the list of models, it just prints it out, prints it out. So this is what I'm doing here. And if you're used to the formatting, string formatting in Python, this should all look very, very straightforward to you. There's nothing extraordinary about it. Okay? And the only reason is this line is surprising is because there is at the end, there is one model which is not a model. So I threw that out. I filtered that out. So now that we have all this model, you have a choice. Which one should I use? And so I'll tell you a little bit about what you can do. You see, here, do you notice that I'm starting with downloader that load glove wiki gigaword 50. Now, by the way, this word downloader is smart. If that word embedding exists on your machine, it won't go and re-download it every time. It will just pick it up from your local directory, from your local host in a standard location, wherever it has stored. It will just go and read it back from there. Right? So it is pretty efficient, but nonetheless, these models are huge. So for example, glove wiki gigaword 50, the way to interpret it is that, what is the algorithm? So let's go and look at the model. The first word is the algorithm. It is the fast text, one of the algorithms we talked about. Remember, fast text deals with word pieces, subwords, right? A character level things. Word to vec, we know ConceptNet is another. Word to vec, glove, these are the big guys. These are the big word embeddings we talk about. Wiki news subwords means wiki news is Wiki Foundation has many sites: Wikimedia, Wikipedia, Wiki this, Wiki News, Wiki Book, and so forth. So it seems that they have picked up the Wiki News here. This one I'm not familiar with, so I'll be silent on that. Word to vec, Res Corpora. This is another. There's Google News, Wiki Gigaword, and so on and so forth. Glove, etc., etc. So the last digit, the last is a number. Number tells you the dimensionality of the embedding. So you can see that the dimensionality seems to go from 25 all the way to 300. 300 is about the limit. You tend not to go beyond that. Sometimes, rarely, you see embeddings of 500 dimension also. But 300 has more or less become a de facto standard these days when you are using a pre-trained model. And most of the time, people just end up taking let's say the Google News embedding or the glove, this 100-dimensional gigaword embedding and so forth. So we'll play around with some of these. What I have done is, in these notes, I have commented these three out. I suggest you play around with each of these. A word of caution, the Google News 300-dimensional word embedding is 1.5 gigs. So in your home internet connection, it might take a few minutes to download, and make sure you have that much of disk space. The other ones are smaller, but they're still big enough to download. So be aware that these are relatively big files, like all AI models that we have been encountering in this course. These are relatively big files that get downloaded. Okay? And each file, roughly speaking, logically, is built of a word, its ID, its index number, let's say 1, 2, whatever it is, and then its vector representation, right? That's all it is. So with that, I've taken one particular example.
Asif, is there a frequency at which these, like this is being made available by the creators of GenSim, right? Do they go back and keep updating these word embeddings?
Actually, these are not made by GenSim people. These are trained by a lot of people in the open source community who have made it available. GenSim is just giving you a helper utility to download those.
Okay.
That's all. So the answer to that is, see, this is classical natural language processing. As you will realize, the state of the art has moved forward, right? So we do things when the transformers and attention comes in. You'll realize that in many situations we want to do things differently. People are still creating word embeddings of this kind. These are called like context-free, like basically context unaware, agnostic word embeddings. There's still a body of research that is happening to create better versions of it. People keep training. The amount of activity is enormous. But all these word embeddings, they all look the same. So you notice that somebody has published a paper and created one more better word embedding. It doesn't take many lines of code to download and start using the word embedding.
Okay.
And generally what happens is, that is why if you go and look at your course page, let me take you guys there. If you go to the word in NLP, word embedding section, I want to pay attention to this. Guys, do you notice that I have the initial papers of GLOVE, etc., deep contextual word representations and so forth, NLP, but these are the thing. But if you go and resources on NLP books and resources, you will find a curated list of embeddings. This curated list of embeddings, do you notice that there is a lot of work that people have done on word embeddings? Do you see what a long list of research paper there is? Right? And it goes all the way down to, well, the last one seems to be on 2019, November 2019, spherical text embedding. So there you go, right? Very, very rich amount of literature. What does it take for you to go and get it? Nothing. You just have to go here. You see this training code, the code is available, pre-trained models. So what do we need to do? Suppose you want this guy's embedding, this one is sentence embedding. You click here, and you notice that if you notice carefully on my bottom left-hand corner, there is already a download button. Premjit, can you see that?
Yeah.
Yeah. So I won't download it because I don't need it. So all of these embeddings are available. Go pick and choose. You don't have to go through GenSim. You can just go to the researchers page and they are all making it available. You can just use it from there.
Okay.
Right?
Thank you.
That's that. And it's a very rich world, actually. Like everything in research, any one topic, right? There's a tremendous amount of creativity and many PhDs have come out of it. And every once in a while, somebody, just when you thought you can't do anything new, everything has been done, somebody will do something quite innovative. So it's going on. Huh? So now, anyway, I'll take a word here. Consider the word vector. So let me actually run this. You notice that when you run it, it will load this, even though it has been downloaded on my machine. It takes a little bit of time to load, guys. Huh? So be aware of that. When you run on your machine and you just see a star and nothing happening, it doesn't mean that your code is not working. In my machine, it took 14.7 seconds on my laptop. Your mileage will vary, but wait a bit patiently. Then a pretty large model, word embedding, has been loaded into memory. So I take a word as an example, morning, and I ask this word embedding, find me the most similar words to morning, right? Just to see if semantic, if it is semantically rich. Remember, if you were using TF-IDF or vectorizer, or we were using one-hot encoding or things, I mean, if you're using one-hot encoding, would you agree that no two words are similar at all? The similarity between any two words is zero. So you can't say, you can't ask this question in one hot encoding or the bag of words representation. What is the most similar word to morning? Well, every word is equally similar and not similar at all. Right? But with word embeddings, you can ask these questions. So let us see, when you ask for similarity, you'll come up with some half a dozen or 10 or whatever it is, a small number of, and you can give the number, how many words that you want in the output. So it has found some words. So the word most similar to morning are afternoon, evening, day, night. Right? Look at the first few words. Would you agree that these look similar
Yes.
contextually? Right? They're related, right? They're very related. They're not synonyms, but they are related. Right? Likewise, and by the way, you can play with any other. Does anybody have a word suggestion? Let's say cat, right? It turns out that dogs, right? Both of them are pets. Rabbit is the next thing that people like to keep as pets. And it shows up here. Or we could take, I don't know, what can I take? Hammer. Now let's see what is, I've never tried hammer. Let's try that. Arrow, stick, thrower, sticks, metal, bolt, nail is somewhere there. Nails. So there we go. So anybody else has a suggestion? We can.
Unicorn
Unicorn.
is not found in the vocabulary for me.
Okay.
Can you try happy? It kind of throws some interesting words there.
Yes. So look at this unicorn. Yes, it seems to have thrown Medusa, dragon, beast, lion, mermaid. Yes, all imaginary creatures. Ninja, vampire.
Or the heterosidicity.
That is, I doubt that would be in the vocabulary, but you want to give it a try? Let's try that. Word not found in the vocabulary. That, by the way, that is me putting a try-catch block. If you don't, it will throw an exception saying that word is not found in the vocabulary. So let's try residuals. Debits, airtime, freebies, etc., etc. So you can play with that. I'll just leave it with morning. And
Let's try vodka, sir. Vodka one time.
Which one?
Vodka.
Vodka. You seem to be fond of vodka. Ketchup, beer, cognac. The first one, I don't know why ketchup is similar to vodka, but cognac, tequila, distilled champagne whiskey. You see that these words are related. They are all alcoholics. Except
Maybe
for
also
ketchup.
word not found in vocabulary. Just rerunning that cell with a different word.
Sorry,
Ketchup might be the poor man's Bloody Mary.
Oh, ketchup may be the poor man's.
Ew, gross.
Yeah. Oh, by the way, there are two kinds of similarity measures. The other one is cosine matrix, cosine similarity. Let's try a luck with that. Vodka has nothing found. That I'm surprised with. Let's say unicorn. No, I don't know. Oh no, mult, cos mul rather, multiplication. Medusa, dragon, beast, lion. So there are a couple of similarity measures. You can do the Euclidean similarity, you can do the cosine similarity, and so on and so forth. So those are the options that you have. I'll leave it as unicorn. Let's find out the similarity between king and queen. Do you notice that it comes out to be 78% similar, right? The ordinary Euclidean similarity, and what happens if I do the cosine similarity, then it becomes, what did I do? Actually, I'll have to look up the exact syntax for this. So let me leave it as that. similarity.
Why would I get word not found in vocabulary for unicorn when you get a nice list like Medusa, dragon, beast, etc.?
No, you don't find. Actually, I made a mistake. Word most similar is coming out, right? Word not found will happen only when you put something that is truly not there. You're asking why I got that at one time. Kate?
Oh, okay, what was,
No, because I made a typo and that caused an exception.
oh, was there,
Yeah, I just made a typo, and so that made it go into the exception block. It isn't real. So unicorn is very much there in the vocabulary. So between man and woman, as you notice, 88 and 78% similarity between king and queen. Perhaps ordinary people are much more, should we say, having better married lives than kings and queens? I'm kidding.
yes.
So, and then I talked about this fact that with word vectors, you can do this vector arithmetic. So you can do king minus man plus woman to see what happens. So this is it. You're saying the positive terms are, you can imagine this sentence to be plus king minus man plus woman. So the positives are king and woman and the negative is man. And then you ask, if I give this kind of a syntax, this is your basic analogy experiment, right? So a king is to man, what is it to woman? That sort of thing. And see what is the answer it throws up. Do you notice that it throws up queen as the first answer?
Can I see your text before that has the unicorn for another moment, please?
This one?
Yes, thank you.
Let me know when you are done looking at it.
Can you point out where the typo was? Because
Oh, the typo that I had made was this. Let me make the typo again. Cos mat. I said cos mat rather than mul. It was a typo on my behalf. And so we ended up with this, a word not found in the vocabulary. So the thing is there are two distances, Euclidean and cosine distances. Cosine is given by cos mul. And then obviously if I give either cos mul or Euclidean, if I don't make the typo, I don't get the exception. Remember, except is causing this word to be, this sentence to be printed, a word not found in the vocabulary. Did you get that?
I'm still getting that word not found in the vocabulary. I'm not.
Where are you getting it? Are you looking at my screen? Is everybody seeing that?
I think she is trying on her machine, sir.
Oh, you're trying on your machine. Then, and did you include this? Which are you using this word vectors?
Yes, I'm using that same first one.
All right, so let's take it offline, guys. I'll help you, Kate. After in the break, maybe I'll help you with that, and see what in the world is going on. Should anybody else is able to reproduce the problem?
No, it works for me.
It
It works
works.
fine, Kate, when I'm trying unicorn.
So Kate will take care of it in your machine in the break. So guys, this is the thing that got people initially quite interested. A king minus man plus woman, as you can see, is the queen. It suggests the queen. And likewise, comparing Rome and Paris, what are they? They are both capitals. So here's the thing. If you take Italy and you subtract Rome, but you add Paris, what do you get? You get the country France. Do you notice that the first match is France? Isn't it interesting? A word to vec or a representation is, at the end of the day, it is nothing but a rather compression, summarized representation of word vectors based on the corpus that it has been trained on. And yet it seems to be semantically rich, right? It's a quite an interesting thing. That's what got people very excited a few years ago. So you can, by the way, try a different similarity measure, cosine mult, right? So there's the Euclidean and the cosine distances you can play around with. And the same thing you can do with the cosine and you get pretty similar results. Then the other interesting thing you can do is you can find the odd man out. So if you guys look at this, cow, horse, bird, giraffe, donkey, buffalo, ox. I just wrote down the names of some animals. Can you tell which is the odd man out?
Bird.
It's yes. And lo and behold, it has on the other hand come to the conclusion that it's buffalo.
Well, I think the two-legged bird versus the four.
Yes, that's true. So, and this shows actually the limitation of this kind of learning just from a corpus. What happens is that buffalo is not commonly used in a lot of the English literature. Actually, it is mostly the Asian countries that talk of the buffalo. They would consider the cow and the buffalo together. In my childhood on my farm, I used to have both cows and water buffaloes. Right? So obviously, if I have to look at this list, based on your context, I would consider giraffe to be out of place because on my farm, I had everything. I had a cow, I had cows, I had horses, I had birds, I had donkeys, I had buffaloes, and I had ox. But what I didn't have was giraffe. And so it depends upon how or what corpus it has been trained on. So suppose I now make it a hammer. And now let's see what happens. If I make it a hammer, it will immediately identify the hammer because the hammer is really far off from those animals, isn't it? Or suppose you take Trump and see where he stands. Well, it turns out that Trump is an animal after all. No, I'm kidding. I'm joking. So, okay, here we go. That explains that sentence similarity. So you can also see the similarity between sentences. You give a sentence as a list of words, a list of tokens, and two sentences as two lists of tokens, and it will compare them. These are again things you can do with word embeddings. So here it is. This is the word mean distance. Right? What is the distance between the two sentences? It turns out that you have to know how to interpret it. This is a much smaller distance. It was the best of times. It was the worst of times, the famous starting lines of Charles Dickens' Tale of Two Cities. So you get a much smaller distance. Then I take another sentence, somewhat related. The first sentence is, it was the best of times. It was the worst of times. And the second sentence I have is, which is not Charles Dickens, it is something that I wrote. Once upon a time, citizens could elect their president. And so the word distance is much longer. Right? And then you can take another two sentences. The first is, this is a very technical sentence, word embeddings are efficient latent representations. And the second sentence is, in a previous era, citizens could elect their president. Right? And so you can see that the distance is much larger between these two things, clearly. So let's go through this. It is the best and worst of times. There's just one word difference. You can imagine that the mean distances would be close. And also best and worst, to the extent that they're superlatives, they're pretty close in the embedding space. So they are close. This one, though, there's significant distance. We are talking about citizens and president and so forth. So the distances increase, the distance increases. And then I take two sentences. One has absolutely nothing to do with the other. And you notice that the mean distance between the sentence increases. So do you see, guys, how you can compare? So if you had to pick, let's say that this word, if I took two sentences, one from each subject, one from chemistry and one from politics, or two sentences from politics and one from chemistry, can you tell them apart? Right? Can you group them together just by looking at their distances? The distance of the chemistry sentence to both the politics sentence would be much larger than the distance between the two politics sentence, isn't it, guys? So you would conclude that the two politics sentences are about the same subject. So that's how you can use word embeddings, quite useful. Now, sometimes what happens is, here is one thing that you can do. Suppose you want to tell if two articles are, like if you have three articles or something like that, and you want to see how similar are the articles to each other. What you can do is you can obviously tokenize, extract the keywords, get the article into a list of words. So I have baby articles. My article contains just two words, glowing bulb. The other is the shining sun, and the next is the hammer nail. So when I compare the word embeddings for this, what does it say? Sorry, the word similarity between the words. We realize that, and the method that you use is N similarity. And different libraries have different methods, but all NLP libraries give you something. So bulb, the first sentence, which is about bulb and the sun, do you notice that their similarity is much higher, twice as much as the similarity between the sentence about the sun and hammer?
Yeah, the bulb-sun similarity would probably be even higher if bulb didn't also have a meaning of a plant bulb.
Yes, that's true, right? Or what happens if we replace it with lamp, glowing lamp? Well, it more or less remains the same. Well, there we go. Right? So anyway, what I'm trying to show you is that word embeddings have a rich semantic structure that you can exploit for your tasks. One easy way to find out if two articles are related is just by looking at, extract the keywords and look at the similarity. Or one thing you could do, which is very useful. Suppose you have a lot of articles. It's sort of a rough measure. They all deal with the subject X. What can you do? You can create, extract all the keywords that you find in those articles, then create the average, the mean vector out of those keywords, the centroid of those vectors, those word vectors. You can find the centroid, which would be the mean. Once you have found the centroid, what can you do? If you get an article and you want to determine, so suppose you have two subjects, subject A and you have found the centroid vector here, and subject B and you have found the centroid vector here. And what you want to do is you get a probe, you get an article and you're probing, does it belong to subject A or subject B? So how would you do that? Would somebody suggest?
One more time,
What's that?
restate, please.
See, suppose you have already learned two subjects, let's say sports and let's say science, right? So you take all the articles that belong to sports, you extract the keywords out of them. Now each word will have a word vector. You find the centroid of those word vectors. What will you know? You will get to the essence, the central location of that subject, sports. Now you go to this, all the articles that belong to science. Once again, you extract all the keywords, take all the nouns and so on and so forth. Then what do? You find the word vector, take the word vectors and find the centroid of this subject too, science. So now you have two vectors, and one vector pointing to the centroid of sports, one vector pointing to the centroid of science. Suppose I give you a document, a new article, and I said, tell me whether it is science or sports. How would you do that? Anyone?
Compare it to the centroids. Like take the centroid of the new document and compare it if it is closer.
Right. What you do is you create this document vector. You take the keywords. You find obviously the centroid or the mean vector of this one, and compare it. How do you compare it? Just using similarity, right? Find, is it more similar to this or more similar to that? So whichever one it is more similar to, you can classify as belonging to that subject. Am I right? Are we getting it, guys? It's a very simple way of determining what a particular article is about.
So Asif, can we use the LDA? Like,
No, see, that is a different approach, isn't it? If you're doing latent dirichlet allocation, you are doing a topic modeling, two topic modeling, and so on and so forth. Right?
oh, okay, got it. Yeah.
I'm giving you a much simpler, a different method, which is much simpler. Right? Now, whether it is effective or not is a different question, but it certainly is a viable approach. You just find the centroids of the subjects and then you allocate, you determine whether a word vector, an article belongs to this or that. You see how straightforward it is. Now, how do you extract the keywords? A very simple brute force approach would be to use the NLP. Remember that part of speech. So keywords are what parts of speech typically?
Verbs, noun.
Verbs and nouns, right? Pick up the verbs and nouns, right? You build a knowledge graph out of a subject, verb, object, right? So you can pick up the verbs, and then out of verbs, you have to be careful. You don't want to take very common words. You have to filter out the stop words. And then those verbs, then you have, right? Then you have all the keywords of the subject. Once you have the keywords of the subject, all you have to do is create their mean vector or the centroid of all the words. It is a rough and ready way for you to tell whether an article belongs to it or not by just looking at the distance of that article to this centroid, right, to this mean vector. You see how it is. And so, guys, this has direct bearing on the project you are doing. Hint. If you, I hope you guys are making progress on the project, because I'm going to start releasing pieces, bits and pieces as solutions to the project soon. So use that, guys. Huh? So that is word similarity. That now looking at a vector, by the way, now you can choose to just see what a vector looks like. So how do you see a vector? Actually, let me break it up into two parts. Let me split it. Split this and X. What does it look like? Of course, it looks like this, you know, which we took as 50. I think we took a 50 dimensional embedding to play with here. Did I not? Yeah, 50 dimensional. So you would agree that this vector that I have come up with is 50. 1, 2, 3, 4, 5, 6. 6 times 1, 2, 3, 4, 5, 6, 7, 8. 8, 6, yeah. 48 plus 2, 50, yes. And so one thing is there, when you get a word vector, it is not normalized. Remember, these vectors are not unit vectors. Are we together? So in the latent factor space, two vectors can be collinear, but they may be of different sizes or almost collinear, and they may be of different sizes. In that case, the Euclidean distance would be pretty significant, even though the cosine distance would be very low. Do you see that? If two vectors are collinear, one is, let's say, 10 times the other, you still have a significant Euclidean distance to traverse, but the cosine distance, the angular distance between them, is very, very small because they're collinear. They're close to zero. Am I making sense, guys?
Yes, sir.
Yes, good. Anybody has doubts, please stop me at this moment. So one of the things I wanted to show you is, given a vector, if you do, how do you find a rough and ready way to find the magnitude, or rather the square of the magnitude of a vector is simply to dot product it with itself, right? So if you dot product it, then you see that it is actually 26.3. It will be some arbitrary number. You do it for horse and it will be something else. Now, if you want a normalized version, you don't care for the Euclidean distance, you care only for the cosine similarity between words. One of the things you can do is you can use the norm. You can use a normalized version of the vector. When you take a normalized vector, what is the normalized version? What does it mean to normalize a vector, guys? Who would like to enlighten me?
Is it like same scale?
It adds up to 1.
Divide by the
Yeah,
magnitude.
all of you are saying the right thing. I would like to hear it in a more mathematically precise manner.
Magnitude is 1.
Magnitude is 1. So what you do is you take the vector and you divide it by its magnitude. Then you sort of scale, I mean, sort of you scale it down in such a way that it becomes a unit vector, right? So when you have a unit vector and you dot product it with itself, you will get 1, right? So another way roughly to think about it is that it is a point on a sphere, on a 300 dimensional unit sphere, right? All the words are little points on the sphere. And the only thing you care about is the cosine distance between them, right? That brings me to the question, what is cosine distance? Anybody remembers? What is the cosine distance between two vectors?
The shadow of one vector onto other.
The projection.
A dot B by magnitude of A.
The cosine similarity of two vectors, A and B, is A dot B divided by the magnitude of A and the magnitude of B. Because A dot B is A magnitude of A, magnitude of B, cosine theta, angle between them. So the similarity, the cosine theta, right, is the measure of similarity. The smaller the angle, the more the similarity. So the cosine similarity is A dot B divided by the magnitude of A and the magnitude of B. Let's scale that. Normalize, basically the dot product between the normalized A and normalized B. That is cosine theta. That's a measure of similarity. And distance, when we speak of cosine distance, it is 1 minus cosine theta. Right? So 1 minus similarity is distance. So that is the cosine distance. So yeah, there you go. Whether you speak of cosine similarity or cosine distance, it's a matter of convention. One is just 1 minus the other. So if all the points are dots, if all your words are dots or points on a unit sphere or hypersphere, then you can, the only meaningful notion of distance you're left with is your cosine distance, right? Or similarity, the angle between 2 points. Are we together? That's that. So the next thing, and this is the last thing that I'm going to talk about, because today is a small session. So you say, oh, okay, all that is very fine. I have been using other people's embeddings and I've been using it. What if I want to build my own embedding from scratch? So I'll show you the code of how you build your embeddings from scratch. So what do you do? So by the way, Gutenberg, how many of you know what Gutenberg is?
Original printing.
Gutenberg printing press, of course, is the first printing press that started the whole revolution of books and learning. But there's a Project Gutenberg. What Project Gutenberg does is every single book that is beyond copyright. So a book that is more than 100 years old, by definition, is beyond copyright. So it takes every book that has either been donated to open source or is beyond copyright because of being too old. They have collected it. Most of the great classics are there. They have collected it and they have cleaned out the text, a tremendous amount of effort, cleaned out the text and made it available in text and EPUB for your e-reader and HTML format. And it's one of the most wonderful projects. Everything legal, and it is the whole spirit of creating the commons for people, shared commons for people. So from that, we are going to take a few novels. These are all the great classics at one time, for those of you who are quite young. Jane Austen was a British writer, very famous. She wrote lovely books, Emma, Persuasion, Pride and Prejudice, Sense and Sensibility, and so on and so forth. Blake was a poet, right? Bible hardly needs, a King James Version hardly needs an introduction. Byron was another great poet and writer. Then Burgess I've never encountered, at least I'm not familiar with. Carol, Alice in Wonderland, of course, my favorite. And then you have all this Chesterton humor and so forth. Melville is an American, of course, writer. Milton's Paradise Lost and Shakespeare's hardly needs an introduction. And in US, of course, Walt Whitman's Leaves of Grass hardly needs introduction. So these are the great classics, as you know, and they are freely available as text. So therefore, you can use it for your natural language processing use without worrying about copyright violations. So this is what I've done. What I've done is I've taken this, and by the way, this NLTK comes with it built in. You don't want this, you can just go to the Gutenberg project and download the text file and then yourself break up the text file and play, but I've started with that. What I did is I took 3 of the novels of Jane Austen, Emma, Persuasion, and Sense and Sensibility. These 3 novels are these text files. And for each of these, I got the sentences out of them and I collected all the sentences. So this code, I'll let you just eyeball it for a moment, but you'll realize that I'm not doing it. The only thing mysterious here is Gutenberg is a library that is part of NLTK, a module. And if you call the sense, which stands for sentences, it will take the file, the text of the file, break it up into sentences and give it to you as sentence. And each sentence, it will give you as an array of words. Are we together? And so just for fun, I printed out the first sentence and it says Emma by Jane Austen, 1816. As you can see, it's a very old 200-year-old story. Right. And still a great favorite amongst people. Okay, so let's go process this thing. Remember guys, when you get text, a lot of the time in NLP goes in cleaning up the text. So what will the text have? It will have words in capital letters, it will have punctuations, it will have strange symbols and whatnot, right? And the words need to be made into the standard form, lemmatized. You need to throw away the common stop words and so forth. So that is what I'm doing. This by now you should be familiar with. It turns out that if I want to use Spacey, I need to rejoin all the words into a common sentence and feed the sentence into NLP. Otherwise, it's very inefficient to feed it word by word. Just for efficiency, I've done it like this. All right. So actually, I could have been even more. I could have just joined all the sentences also together and made one long, but I didn't do that. I kept it separately as sentence for reasons that you'll see. So I take each sentence and I clean it up. I take this token, go to the lemmatized form for the token, and keep it only if it is not a stop word, means common words, and if it is not in these square brackets and underscores and so forth, and it is not a punctuation, exclamation mark, full stop, comma, etc. And it is not a symbol. So I'm just doing basic cleanup, guys, and you'll realize that this weeds out a lot of the junk. And then I print out one of the clean sentences. Emma Jane Austen, 1816, right? So if you compare this with that, you'll realize that this unnecessary begin bracket, end bracket, these are not really words, disappears. By is a stop word, it disappears. So you take the clean text and then I randomly took one more text. 152 has no meaning. Huh? You can put whatever number you like. And here comes a sentence that seems to make sense. Emma think good probably means Emma thinks good, or rejoin Mr. Woodhouse, understanding, and so forth. These are the words in the text. Then now that you have words separated out in the sentence, now you notice that I'm create a word. By the way, word to work. So your assignment is to do glove and fast text on it, homework. So if you can please note it down. Take the same notebook, but instead of doing word to vec, replace it with glove. These are just one word changes. And see how different or how useful it is. Do you get better results if you use a glove? Do you get better results if you use fast text? Are we clear on the homework, guys?
Yes, Asif.
Yes.
Try the different word embeddings, try glove and fast text instead of word to vec.
That's right, that's all. And it is as simple as just changing the constructor and a few of the arguments, that's all. So I'm giving you the sentences. Now, when I'm saying size is equal to 25, I'm saying make it of 25 dimensions. Why? Why did I choose such a low dimensional representation? Because, I don't have enough text. The three novels of Jane Austen is still not enough text. You typically look for like a ginormous amounts of text in your corpus to train a proper word embedding of 300 dimensions and so forth in general. So take a small size. By the way, if you take it to be 100, you can play with it, 200, 300, you can play with it and see how you get. The other thing I did is notice that minimum count, I made it 10. And this is something you play with. Why did I take 10? I just said that if words don't occur at least 10 times, they're not useful to me, right? Because I happen to know what Jane Austen's novel contained. So rare words are likely to be typos. It's literature. It is not some science or STEM field or something. In literature, the writers they create the craft with simple words, straightforward, common words. So there we go. So, and of course you can save it and then you can load it back. This is the point that I was making, guys. Do you notice that Word2Vec, I'm not using the model directly. I'm using the model.wv, which is a more immutable but faster version of the thing, a more memory efficient version of the thing. And so what is the difference? If you remember the story, it's about Jane Austen's novel are all about young girls and their suitors, the people they fall in love with, are people who fall in love with them, right? And the whole journey of they getting married and so forth, all the tumultuous romantic years of young people. So, well, that is that. So I'm taking two words, mother and daughter. As you can imagine, in all of this mix, always a mother is involved. So the similarity between mother and daughter seems to be pretty high, 98%. On the other hand, if you take two random words, I just took injustice and Eliot, the similarity is low, it's 0.56. Actually, it was hard to find words which were even less similar. I couldn't. Every two words seem to have reasonably high similarity. So from that, I concluded. And if you look at the word mother and you say, what are the words most similar to it? You get encounter, husband, errand, acknowledge, etc., etc. Not very impressive. Anybody feels that these similarities are impressive?
Not really, no.
Not really, right? And so let's go and play with this. Suppose I change this to, instead of the common dimension that people take is 300 dimension, and quite often they take minimum count as just 1. And let's see what happens if you take default values like that. It takes a few bit to, well, on my machine, it just took 1.58 seconds to train. Why? Because, the corpus is very small. Similarity between mother and daughter is 99%. Similarity between, it turns out injustice and Eliot was not a paradigm of injustice, by the way, in their stories, but for whatever it is 78%, not a good sign. And if you look at the words that are very common to mother, this time it is actually reasonably good. It has come of its sister. Moment marry, and there's a character there. So, you can play around with it. But what is disturbing is the word admiral has up to 3 significant digits, the same similarity as sister to mother. You notice how all the words seem to have more or less the same similarity, right? So it is surely not doing a very good learning. And this is where you play with it. And if you do a different similarity measure, the cosine word, then again, you come up with this sister, moment, marry, pretty much the same answer. But all of them, every single word seems to be similar to the main words. If you want to see what are the words in the vocabulary of your embedding, you can always, of course, call its vocabulary and check it out. And what does a vector look like? This is how a vector looks like it, right? This is your 300 dimensional vector, which is very, very hard for one to play with. And now let's try something different. Go back and change. I will change the minimum count to, let us say, at least, okay, maybe I'll leave it as that. And let's see what happens if I make it something like, pick a number, guys. Any suggestions?
20.
20. And I leave the min count there. Let's see what happens. Mother and daughter remain very similar, but injustice and aliot still are rather annoyingly similar. Mother is similar to sister. Well, mothers tend to deprive. I'm sure every daughter feels that mothers deprive them of something during their growing years. And there you go, mother, sister, deprive. What is the word vector? It is this. And by the way, what other words are similar to this? Sake? I don't know why. Law, mother-in-law, I suppose. Comfort, husband, writing, somewhat useful. You notice that if you reduce the dimensionality, things get better actually. And obviously you can't make anything from the vector.
If you reduce the window to 3, then the Elliott injustice thing goes down.
Right? Yes, and this is another thing to play.
And maybe the size to 100.
Yeah. So let's see what happens. So let's go back and see what happened. Obviously, mother and daughter remains pretty similar.
You need to increase the size to 100.
Oh, you mean you want me to increase the size back
size to 100 and minimum count to 10.
Yeah, minimum count to 10. Yeah, so you can play around. This is great that you're playing around with it. And you notice that the word vector similarity has become this. Now, this is good, I, moment, etc. These are all the words that tends to keep coming up. And if you do it to 25, actually what I'm trying to do is reduce this value. If you were trying to reduce this value, let me take about 20 for what it is worth. Yeah, this has reduced a little bit, but mother and daughter have come rather close. So, you know, these are the games you can play. I'll let you play with these. And with that, this is it. Today was a simple, short day. This is your lab. So guys, go play with that. Now, what I will do, I'll take another 10, 15 minutes. We haven't had a break today. I'll just summarize it. This is classical. Everything that we did in the last 4 weeks is, I would still say, the before transformer world or the classical NLP world. It is using deep learning, yes, but it is not using transformers or attention. In the weeks that will come after Thanksgiving, therefore in the month of December, I suppose, we will be doing natural language processing with attention and with transformers. And those are game changers. This current way of doing word embeddings has one limitation. Take a word like apple. Apple can be close to orange, it makes sense. But apple can also be close to computer. Now the thing is that also makes sense. But in a world, in a sentence where apple is close to orange, it shouldn't be close, computer shouldn't be nearby. Whereas in a sentence where apple is close to computer, these fruits, oranges and bananas, should be pretty far away, isn't it? So in other words, apple is a homonym. It has multiple meanings. Same word with multiple meanings. What you really need is a differentiation between the two meanings of the word apple. And those two meanings should occupy different places in the embedding space. And the word, which word one you pick, which meaning vector you pick, has to be based on context. That context awareness is what you get when you use transformers and so forth. And so as we go from the next week onward, you'll notice that we will retrace much of what we have done in classical NLP, what I call classical NLP. By the way, it is my word. It is not a word that other people use. But this, what I call classical NLP now, the pre-transformer world, all these approaches will retrace it with transformers. And when we do it, you will see how, or what is the value that transformers or attention bring to the table and how they change the game. Having said that, it doesn't mean that we have wasted 4 perfectly good weeks. Everything that you have done is widely used and should be used quite a bit. You should never abandon these classical approaches. It is, remember the no free lunch theorem, nothing guarantees that any one approach is always better than the other. Right? Also, the efficiency part, the computations are very, very cheap and fast with word vectors. right? So do use those. And even though these are sort of universal word embeddings, not context-specific word embeddings, they are still very useful. Right? So with that, guys, I'll end today with the everything pre-transformer. To summarize, in the 4 weeks of NLP, we covered the NLP fundamentals. We did topic modeling. We took a digression and we did the whole series of bottleneck methods. In particular, we learned about autoencoders. We learned all sorts of autoencoders, the standard autoencoders, which are the vanilla autoencoder, the denoising autoencoder, the patching autoencoder, the sparse autoencoder. There's one more, the contractive autoencoders that I didn't cover, but it's there. What it does is that it comes up with a very stable lower dimensional representation of data. Then we did variational autoencoders, which are actually in many ways fundamentally different from other autoencoders, even though they share the same architecture of encoder decoder. In particular, they are not discriminative models, these are generative models. We talked about it and we used the notion of KL divergence, of how you can approximate, you can take the probability of the Z given an input, and if you like, you make that into mixture of Gaussians instead, and you use that to approximate the posterior, namely given an internal representation, what would be the output, right? So, well, obviously I'm using words like prior and posterior. They all come from Bayesian inference. We covered that. I won't cover that in more detail. It gets a little bit technical, but we did go through the technical details. If you watch the prior video that is there on the website, we talk about the Bayesian inference that goes into the heart of variational autoencoders. Now, the point of variational autoencoders is that they are generative models. Once you have a variational autoencoder, you can create new faces, new data, new things. Right? Quite a bit. You can even you can use it for data augmentation. That's a strength of variational autoencoders. And then finally, we did the word embeddings as another example of bottleneck methods. We did, in particular, 4 methods. The continuous bag of words, we did the skipgram, we did the fast text. Glancingly though, just mentioned that you deal with word pieces. And then we did glove. But that's not the limit of word embeddings. There are many, many word embeddings, as we just saw in the list on that website. People keep coming up with different algorithms for word embeddings. And then there are 2 kinds of word embeddings, context agnostic and context aware. We have done context agnostic word embeddings so far. Right? So guys, at this particular moment, to sum it up, you should feel comfortable in dealing with all the common tasks of natural language processing. Right, with this knowledge, right? We did transformers in the previous part 1, and of course, if you remember that, and you still remember all of that, you are pretty much done. Like pretty much, you have understood all of NLP. In the coming 2 weeks of NLP transformers, I will just go. Maybe I'll give 1 week or 2 weeks, depends upon the time we have. Because if you're giving 1 week off, I might not. We're running a little bit out of time. But in any case, transformers change the game. Yeah, we'll probably need 2 weeks of NLP in transformers. We'll do it in greater detail. I'll explain the theory of the transformers more. The lab will do more language translations, more of this, and we'll also learn to train the transformer. So far, we have not trained a transformer. We have used pre-trained transformers in part 1 and applied to our use cases. Now in part 2, we will learn to train the transformers and attention and so forth, and also learn to hybridize them with RNNs and do interesting things. Now, transformers will carry forward with us to computer vision or to image process, which will be the part after that. So that is that, guys. We have finished 10 weeks of this workshop. I'm done, guys. If you have any questions, you can ask me. I'm going to stop the recording.